In this video, we're going to introduce and discuss the concept of degeneracy for basic solutions. First, we're going to define this concept for general form polyhedra, and then we're going to specialize it to standard form polyhedra. So let's consider general polyhedra. In a basic solution, we have n linearly independent active constraints. While we can't have more than n linearly independent active constraints, since our space is Rn, it still can happen that the number of active constraints is greater than n. And this is exactly the case that we call degenerate. So let's formally state it. A basic solution X in Rn is said to be degenerate if more than n of the constraints are active at X. Let's immediately see some examples in dimension 2 and 3. In dimension 2, as always, we visualize the given inequalities with lines, and the constraint is active at the point if the corresponding line passes through such a point. So in dimension 2, a basic solution is degenerate if it is at the intersection of 3 or more lines. In this example, the degenerate basic solutions are C, since there are 3 lines passing through C, and D for the same reason. You can check one by one that all the other basic solutions in this example are non-degenerate. In dimension 3, inequalities are planes, and the constraint is active at the point if the point is in the corresponding plane. In this example, in dimension 3, we have a total number of 5 inequalities that define this pyramid, and the definition of the degenerate basic solution asks for a point to be at the intersection of 4 or more planes. So in this example, the only degenerate basic solution is A, and it is at the intersection of exactly 4 planes. Degenerate basic solutions can strongly affect the behavior of linear programming algorithms, and especially of the simplex method that we will see in chapter 3. We saw a couple of examples of degenerate basic solutions from a geometric perspective, meaning that we just looked at the picture essentially. Now let's see an example where we instead look at the system of linear inequalities, so more from the algebraic perspective. Let's consider the polyhedron P defined by this system over here. And let's consider the vector 2, 6, 0. This polyhedron is in dimension 3 because we have exactly 3 variables. And let's consider the vector 2, 6, 0. You can check that at this vector there are exactly 3 active constraints. These are 1, 4, and x3 greater than or equal to 0. Let's just check one of them. For example, the first, we have 2 plus 6 plus 0 is equal to 8, so 1 is active at our point x. You can also check that these 3 constraints are linearly independent. Therefore, our vector x is a non-degenerate basic feasible solution. On the other hand, consider now the vector x given by 4, 0, 2. You can now check all the inequalities and see that there are 4 active constraints, 1, 2, 3, and x2 greater than or equal to 0. Among these 4 constraints, 3 of them are linearly independent, and this implies that x is a basic feasible solution, but it's also degenerate because the active constraints are 4 instead of 3. Similarly to what we did for basic solutions, I want to obtain an equivalent definition of degeneracy for standard form polyhedra. What we have to do is fully understand the definition of degeneracy in general form polyhedra for polyhedra in standard form. In a polyhedron in standard form, all the equality constraints are active at every basic solution, and we have exactly m such equality constraints. In a standard form polyhedron, all the other constraints are non-negativity inequalities. From the definition of degeneracy, for a basic solution to be degenerate, we need to have more than n active constraints, which then means that we need to have more than n minus m variables at 0 level. And this directly leads us to the definition of degeneracy specialized for standard form polyhedra. Consider the standard form polyhedron P given by Ax equal to B, x greater than or equal to 0, and let x be a basic solution. As always, we assume that the number of rows of A is m. Then the vector x is a degenerate basic solution if more than n minus m of the components of x are 0. Let's see now an example of the generate basic solutions for standard form polyhedra. Let's assume in this example that our matrix A is this one and that our vector B is this guy over here. Since we have 4 equality constraints, in order to obtain a basic solution, we need to select 4 linearly independent columns of A. So let's select columns 1, 2, 3, and 7, which are highlighted here in blue. Now you know very well how to compute the corresponding basic solution. We set to 0 the non-basic variables, and then we solve the remaining system of equations to obtain the basic variables. If you carry out these computations, you will find that the corresponding basic solution is this guy over here, which is 402,0006. By the way, since all the components are greater than or equal to 0, this is also a basic feasible solution. Now we should check for degeneracy. This is a degenerate basic solution. Why is that? Because we have 4 variables that are at 0. And 4 is strictly larger than n minus m, which for this problem is 7 minus 4, because you have 7 variables and 4 equations, which is equal to 3. Let's consider now a different basis for the same example. Now I select the linearly independent columns A1, A3, A4, and A7, which are again highlighted in blue. By the way, this basis is adjacent to the previous one, because in order to obtain it, I simply swapped the second column with the fourth. The corresponding basic solution you can check is this vector x over here, which is 402,0006. This is exactly the same solution that we obtained with the previous basis, and we've already seen that this basic feasible solution is degenerate. In this example, we have not only seen an example of a basic solution that is degenerate, but we have also observed an interesting phenomenon. Namely, this degenerate basic feasible solution can be obtained from 2 different bases. Actually, it was really easy to obtain this example, so let's go back one slide. Here we have the first basis that we considered. Using this basis, the non-basic variables were these 3 zeros over here. These 3 zeros are exactly the n minus m zeros that we should have in any basic solution. However, this solution is degenerate because we have one more zero among the basic variables. Then, in order to construct another basis which leads us to the same basic feasible solution, we made the second variable non-basic by eliminating the column 2 and instead selecting a column among the remaining 3, which is linearly independent from the remaining basic columns, which were A1, A3, and A7. And in fact, we chose A4. With this new basis, we obtained a corresponding basic solution. Of course, all the non-basic variables are 0, and now these are x2, x5, and x6. And solving the corresponding system of equations, we obtained the basic solution, which turned out to be exactly the same as the previous one. This example also suggests that we can think of degeneracy in a little bit of a different way. We pick a basic solution by selecting n linearly independent constraints to be satisfied with equality. We obtain the corresponding basic solution, and then we just realize that certain other constraints are also satisfied with equality. For example, in this two-dimensional picture over here, let's say that we select this linear inequality and this linear inequality to be satisfied at equality. The unique point that does, which is then our basic solution, is at their intersection, and it just turns out that also this horizontal constraint is active at such a basic solution. From a probabilistic perspective, this is extremely rare. In fact, if you generate at random the data of your problem, so the matrix A and the vector B, this happens with probability 0. Similarly, if you are considering a problem that has a degenerate basic solution, then if you select one of the constraints that is active at your degenerate basic solution and you slightly perturb the coefficients of this constraint, then degeneracy disappears with probability 1. So these two observations tells us that maybe degeneracy is not so important because essentially it never happens. However, degeneracy is much more important than what it seems. In fact, in practical problems, the data A and B is definitely not chosen at random, and it always has a very special structure that comes from the real-world problem. And it turns out that this very special structure often leads to degeneracy. So in practice, degeneracy is very common. Next, I want to visualize degeneracy in standard form polyhedra. To do this, we assume n minus m equal to 2 so that we can visualize these problems in dimension 2. Here we have a very simple example. Where we have 3 variables and 1 equality constraint. In fact, n minus m is equal to 2, so we can visualize it in the plane, and we have the 3 non-negativity constraints xi greater than or equal to 0, which then give rise to a triangle. Recall that in a non-degenerate basic solution, then exactly n minus m of the constraints xi greater than or equal to 0 are active. Therefore, our 3 basic solutions are all non-degenerate, because each is at the intersection of exactly 2 lines. Let's now see the next example. Again, we must have n minus m equal to 2 so that we can visualize it in the plane, but now let's make the feasible region a bit more complicated by increasing n and m accordingly. So now we have 6 variables and 4 equality constraints. This means that in our picture we're going to have 6 lines representing the 6 linear inequality constraints xi greater than or equal to 0 for I that goes from 1 to 6. Again, in a non-degenerate basic solution, we have exactly n minus m, therefore 2 of the constraints xi greater than or equal to 0 that are active. So in particular, our vector A over here is non-degenerate, while our vector B here is degenerate because there are 3 lines passing through B. This means, for example, that if you choose x1 and x5 to be non-basic, you're setting them both to 0. The unique point that satisfies both of them equal to 0 is the intersection of the 2 corresponding lines, and such a point must also satisfy x6 equal to 0, giving you a degenerate basic solution. As we have seen also in the algebraic example 2.5, often when you have a degenerate basic solution, there are several ways of choosing which n minus m variables to call non-basic. In this example, the same thing happens. For example, you could choose x5 and x6 to be non-basic, which will give you the same point B, which then satisfies x1 equal to 0. Or you can choose x1 and x6 to be non-basic, and also in this third case, you obtain the same degenerate basic solution B. So also in this example, there are several bases that correspond to the same degenerate basic solution B. The last point that I want to make in this video is that degeneracy is not a purely geometric property. This means that degeneracy of a basic solution may depend on the particular algebraic representation of a polyhedron. Let's see immediately an example. So what I want to do is give you one polyhedron and 2 different ways of writing this polyhedron with 2 different systems of linear inequalities. A specific basic solution will be non-degenerate for one of the 2 systems and degenerate for the other. In this example, my polyhedron is given by this segment that connects the vector 001 and 110. One way of writing this polyhedron is the following. xi greater than or equal to 0 for every I, and then 2 equations, x1 minus x2 equal to 0, and x1 plus x2 plus 2x3 equal to 2. You can check that this polyhedron P is exactly the one that we've drawn in the picture. Note that this polyhedron is in a standard form representation. Therefore, we can use the definition of degeneracy for standard form polyhedra. So here we have 3 variables, 2 equality constraints, and so n minus m is equal to 1. So to understand if a basic solution is degenerate, we have to check if we have 1 or more variables that are 0. Here we have 2 basic feasible solutions, 110 and 001. Now 110 has only 1 variable that is 0, so it's non-degenerate, while 001 is degenerate because it has 2 variables at 0. Now let's get to the next way of writing the same polyhedron P with a different system of linear constraints. Now P can be written as the set of points in R3 that satisfy x1 minus x2 equal to 0, x1 plus x2 plus 2x3 equal to 2, and x1, x3 greater than or equal to 0. The first thing to notice is that this is exactly the same description as before, we just dropped x2 greater than or equal to 0. You should check that indeed the set of points that satisfy this new system is exactly the same old polyhedron P that we have in the picture here. So essentially you need to check that the inequality x2 greater than or equal to 0 is implied by this system over here. The next thing to notice is that this polyhedron is no longer in standard form because we don't have non-negativity for all the constraints explicitly among the constraints. So now, in order to check degeneracy, we need to use the original definition of degeneracy. So we need to check how many constraints are active in a specific basic solution. In particular, the vector 001 is a non-degenerate basic feasible solution because there are only three active constraints, namely the two equality constraints and x1 greater than or equal to 0. So this vector 001 was a degenerate basic feasible solution for the old system and is now non-degenerate for the new system. A natural question that I'm sure you have now is it always possible to get rid of degeneracy by dropping a number of inequalities? After all, this is possible in the example we have just seen. However, unfortunately, this is not the case. In fact, I challenge you to construct a polytope with a basic feasible solution that is degenerate in every possible representation. The hint is that you can't construct such an example in dimension 1 or 2, you need to look at dimension 3. It turns out that actually the reverse can always be done. You can make always a non-degenerate basic feasible solution a degenerate basic feasible solution. Let's see how we can do it for standard form polyhedra. So here we have our standard form polyhedron P given by, as always, ax equal to b, x greater than or equal to 0. Let's say that x star is a non-degenerate basic feasible solution. This means that we have exactly n minus m of the variables xi star that are equal to 0. Now I'm going to write P in a different form, which is no longer, by the way, in standard form. In order to do that, I simply split every equality constraint into the two inequality constraints greater than or equal to and less than or equal to. So I can write P as the set of x's that satisfy ax greater than or equal to b and minus ax greater than or equal to minus b, and x greater than or equal to 0. Now let's just look at the active constraints at my x star vector. I still have the n minus m variable set to 0 because nothing changed among the non-negativity constraint. But now my x star vector satisfies all the equality constraint of the original system, so it satisfies at equality all these ax greater than or equal to b constraints and all these minus ax greater than or equal to minus b constraints. So I have m active constraints here and another m active constraints here. So in total I have n minus m plus 2m active constraints, and that's n plus m, which is strictly larger than n. Therefore, x star is degenerate. Since we chose x star arbitrarily among the non-degenerate basic feasible solution, we have that under the second representation, every basic feasible solution is now degenerate. This concludes our video on degeneracy. In the next video, we're gonna get back to extreme points, and we're gonna give conditions under which extreme points do exist.